This car has begun to accelerate. Here is what the velocity time graph for this car looks like. Looking at this graph, can you explain the velocity time relationship? By using this velocity time graph, you can derive the formulae that show the relationships between velocity, distance, and time. Let us first derive the formula for the velocity-time relationship. The car was moving at a velocity of 6 meters per second. When we start to track its acceleration, the velocity reaches 14 meters per second, 20 seconds later. So, 6 meters per second was the car's initial velocity. We can represent this with the letter U. The final velocity at the 20th second was 14 meters per second. We can represent this with the letter V. The change in velocity is V minus U, which on the graph is represented by the line segment BD. As you know, acceleration is the change in velocity per unit time. On this graph, the change in velocity is BD, and the time taken for this change is the portion OC. So, acceleration is equal to BD divided by OC. By resolving the equation, we get BD equals acceleration multiplied by OC. But BD is actually the difference between the final velocity and the initial velocity. And OC is the time taken, t. So the equation BD equals acceleration multiplied by OC now becomes a proper algebraic expression. This equation represents the velocity-time relationship. If the x-axis represents time taken and the y-axis represents the velocity, then what do you think the area OABDC represents? The area of OABDC represents the distance traveled by the car in 20 seconds. OABDC is a trapezium. So the easy way to calculate the area of this is by calculating the area of this triangle ABD and this rectangle OADC, and then adding the two areas. So the distance traveled is the sum of these two areas. If you examine the equation and the graph carefully, you can see that OA is the initial velocity u. OC and AD both represent the time taken. And BD depicts the result of acceleration multiplied by time taken. So, the distance equation we derived from the areas of the triangle and the trapezium now becomes a proper algebraic expression. Resolving the algebraic expression, we get the equation that represents the distance-time relationship. The area of this trapezium represents the distance covered by the car. Do you recall the formula for finding the area of a trapezium? The area of a trapezium is the sum of the two parallel sides multiplied by half the distance between the two parallel sides. In our velocity time graph, the two parallel sides are OA and BC, and the distance between them is OC. So, the distance traveled by the car is depicted by this equation, which calculates the area of the trapezium OABDC. But OA is the initial velocity, BC is the final velocity, and OC is the time taken. So the distance traveled can be depicted by this equation. Let us look again at the equation for the velocity-time relationship. From this, we can derive an equation for time taken. This is the equation for the distance traveled. In this equation, let us substitute t with the equation derived from the equation for the velocity-time relationship. This is the equation for distance traveled after the substitution. Resolving this, we get this as the equation for distance traveled. This equation represents the distance-velocity relationship.